Yeah, thank you. Thank you very much for the introduction. Thank you for pronouncing my name correctly. And thank you for the organizers for the invitation. So yeah, I'm going to talk about the work that is going to appear with Josef Benna and Severin Lust. And the work is about KKLT and holography. So here we're in Vienna. We are in this landscape versus swampland workshop. And well, we know all from the Swampland that scale separation and de Sitter are hard to achieve in string theory. And actually, in the Swampland, there are even conjectures that tell that it's impossible to get no scale separated ADS vacua and long-lived de Sitter vacua. We all know this, but the landscape tells us that maybe there's a counterexample. Namely that the KKLT proposal by Katru, Kalosh, Linde, and Trivedi, and actually recently like proposed also refined by Andreas and other collaborators. It would be a counterexample to both conjectures. So the KKLT scenario is a two-step procedure. In the first step, one stabilizes the Calabi-Yau fluxes, the Calabi-Yau moduli with fluxes and non-perturbative corrections. One thus gets a supersymmetric scale-separated ADS vacuum with, of course, negative cosmological constant. And in the second step, one raises the cosmological constant to a positive value by, for example, adding anti-D3 branes at the bottom of a wrap throat. And this gives us a de Sitter vacuum with broken supersymmetry. So in this talk, we will study this first step through holography and the main rules. So in the first step of KKLT, what we want to do is to stabilize all of the moduli. And so we have complex structure moduli and Keller moduli. The complex structure moduli control the size of the 3 cycles, and the Keller moduli control the size of the 2 cycles and the 4 cycles. So the complex structure moduli are already stabilized at tree level by the fluxes. And in order to stabilize the Keller moduli, the fluxes when I say the tree level, it means that there is a superpotential Gopakuma-Vafa witten superpotential that depends on the fluxes G3 and on omega 3. So the Keller moduli, to stabilize them, in the end, one needs to add the D3 incessant corrections, which in the end will also depend on the fluxes G3. So here, the non-perturbative corrections have to be exponentially suppressed if you want. They need to be exponentially suppressed. And once we have both of them, we can get a cosmological constant that is in term of this the stabilized Keller modulus sigma 0, if you have one modulus. Yes. Okay, and so because the exponentials are very small, then automatically what you get is that you get a cosmological constant that is very much exponentially suppressed. And this is what we need for the second step as well. Yeah. Right, so actually there is a 3-dimensional version of KKLT, so you could understand that as either a dual or a toy model of that. And so the idea is that you could try to write the same thing by having M theory on Calabi-Yau 4. So then you would get a three-dimensional version of ADS, right? So the Calabi-Yau 4 would be made of the same Calabi-Yau 3 times T2, and the shape of the T2 would be controlled by the axial dilaton. And you would get the same kind of superpotential controlled by a self-dual flux G4. So the G4 would be made of F3 and H3, the type 2B fluxes, and where A and B are the cycles of your torus. So again, you would have the same kind of superpotential that depends on the fluxes, and yeah, again. So from that, one would get a scale-separated ADS3. I have the impression that there is I mean, this is not supposed to appear, right? So I think something is. It is no. I don't understand why. Okay. Okay, now I think it's good. Right. So again, out of this superpotential, one would get a scale-separated ADS3, where here this time the cosmological constant would be again exponentially suppressed. So we can study first this example, where would and the idea to do this with holography is to trade the fluxes with branes. So before I apply this idea to KKLT, I can talk about what would be the flux brane correspondence for branes, for a black hole, sorry. So think about a four-dimensional n=2 black hole. I call this the MSW black hole because from the microscopic side, we understand what is happening. So it's by Mardasina-Strominger-Witten, MSW. And so you can consider a M5 brane wrapping a circle, S1, that I label by Y, and a four-dimensional cycle that is holomorphic inside of a Calabi-Yau threefold. So locally, it looks like something like this, right? So we have time, we have non-compact dimensions, R3, we have this Y circle here that all of the M5 branes are wrapping, and then there is the Calabi-Yau labeled by 1, 2, 3, 5, 6, and so locally, so globally, this is just a single M5 brane wrapping a very complicated cycle. But then locally, if you zoom in at one of the triple intersection locus, then actually you would have like one M5 brane in 1, 2, 3, 4, one other M5 brane at 3, 5, 6, 7, sorry, 3, 4, 5, 6, and the other one at 1 and 2 and 5, 6. And then there is also a momentum, so Kreuzer-Klein momentum, in one of the directions of the S1. You have this brane, you back react, and in gravity that gives you a black hole solution. So the four-dimensional black hole solution, of course, and so the brane system is a point-like in R3, and that gives you a four-dimensional black hole. So from the four-dimensional perspective, there is the attractor mechanism. So it tells you that the moduli are stabilized near the horizon. Moduli Ti and let's say some volume, okay, they're stabilized near the horizon. From the 11-dimensional perspective, this attractor mechanism can be understood as that the shape of the Calabi-Yau is being stabilized near the horizon. And how does it get stabilized? It gets stabilized by fluxes. But you can understand that from a brane perspective, because the brane perspective tells you that whenever you have a parameter that controls the size of one of your cycles, then the size of this cycle is going to be a competition between the branes that are wrapping this cycle and the branes that are orthogonal to that cycle. So the result of this size is the competition between the numbers of times these branes are wrapping orthogonally or perpendicularly to the cycle, or sorry, parallelly to the cycle. And then, of course, we have a black hole, so we have also an entropy that is macroscopic, and you can match it to the microscopic entropy. And from the microscopic point of view, you can count what is the number of deformations of this complicated cycle. And the Mardasina-Strominger-Witten tell you that the microscopic entropy is going to scale like this in the regime where Q is big. So Q is the amount of momentum that you want to have, the amount of momentum that you want to have in this direction. And so it's going to be square root of Q times a left central charge, where the left central charge counts essentially the number of triple intersections that you have, plus some corrections. So this entropy comes from the number of ways to distribute your huge amount of entropy, quanta, so Q, into all of these triple intersections. So each of the triple intersection has some degrees of freedom. You can move the triple intersections. And then you want to distribute all of your momentum into all of these triple intersections. So the number of ways to do that gives you this microscopic entropy. From the four-dimensional perspective, you don't know anything about this, but you can just measure the area of the S2 at the horizon scale, this area of the horizon of the S2 is related to the ADS2 radius in four-dimensional units. So I'm a four-dimensional person. I just measure the size of the ADS2. I have nothing. I don't know nothing about what is happening in microscopically, but I know what is the number of degrees of freedom. The ADS2 is because you have a ADS2 cross S2 near horizon region. Yeah, so yeah. So if you take the time and the four-dimensional, yes, yeah. So in these like big non-compact four dimensions, then you have ADS2 cross S2. Right, so this is the movie that I think we saw. It has nothing to do with the talk except the title. So I like the title. So anatomy of four. So you can apply the same game for the Flux's brane, but for KKLT ADS. And this has been done by Severin Lust, who was here last week. Max, maybe he is here still, I don't know. And Kumul Wafa and Kaishu. So the claim of these authors is that it's impossible to construct a ADS3 vacuum with the Calabi-4 stabilized with arbitrary small cosmological constant. Sorry? Oh, okay. I haven't checked the archive yet. So, okay. Okay, great. Yeah, probably not. Right. So, and the idea that what they did is that they trade the G4 flux, but with M5 branes on orthogonal cycles. And so, because you have a self-dual condition, locally what you see is something like that. So you would have a self-intersecting M5 brane in the Calabi-out directions. So 1, 2, 3, 4, 5, 6, 7, 8. And at z equals to 0, then this would form a domain wall. So from the three-dimensional perspective, that is to say time, y, and z, this KKLT ADS3 would be sourced by the domain wall. So what do they mean is that they can write an ansatz that is governed by some scale factor d of z. Z is this domain wall dimension. And so the scale factor would satisfy a differential equation that depends on the tension of the wall. And the same would happen for the scalars that live on this ADS3. And this tension of the domain wall is related to the difference of the vacuum expectation values of the scalar potential in both sides of the domain wall. And so the idea is if the KKLT solution exists, then at z equals to infinity, so far away from the branes, you should reach the KKLT ADS3. So that's the picture. So you have a supersymmetric ADS3 from M3 on Calabi-Yau 4 in the presence of a self-dual flux, G4. That's very far away from the branes. This is somehow sourced by a domain wall made of M5 branes wrapping a special Lagrangian L4. So you have the typal cancellation conditions, and so on the right side we wanted to have fluxes, but on the other side we decide to, for instance, so here, so that just for simplicity, we want the tension of the wall to be exactly the vacuum expectation value of the right ADS, right? So then we don't want to have any vacuum expectation value on the left side, so we don't want to put any fluxes. But then it means that because you have this typal cancellation condition, you have to replace these fluxes by M2 branes. So there is a so if you look at the world volume theory of the M5 brane, because if you remember well, there was a one common direction between the M5 branes. So there is a 1+1 dimensional effective quantum field theory in the UV, which is supposed to flow in the IR to the CFT that is dual to the supersymmetric ADS3. So at z equals to 0, at the location of the branes, the ultraviolet central charge measures the number of degrees of freedom on the brane, on the M5 branes. But far away from the domain wall, there's another central charge. This one is a infrared central charge, and this infrared central charge measures the radius of the ADS3. It's related to 1 over the cosmological constant. And then these authors in the Harvard group use a C theorem for two-dimensional CFT, which tells you that the central charge in the UV has to be bigger than the central charge in the IR. Therefore, that puts a lower bound on the absolute value of the cosmological constant. And to put this bound, what they do is that they count the possible deformations of the spatial Lagrangian within the Calabi-Yau 4. So this is exactly the same logic as in the black hole case, where at MSW we're counting the possible deformations of the L4, but within the Calabi-Yau 3. So you get this result. So essentially, you can interpret that as that the central charge is given by the number of self-intersections in the Calabi-Yau, essentially, right? And so each of the self-intersection would carry one bosonic and one fermionic degree of freedom. And on top of that, it's not enough because you could have other things that remain. So you would have some independent strips, and the number of independent strips is given by the Betti number, the first Betti number. So this is a way to interpret that result. So then you can show that because this is the number of self-intersection, it scales like a number of flux squared. And this is dominated by the number of flux squared. And so therefore, the central charge that they compute is of order the number of flux squared. And therefore, the cosmological constant has to be bigger than 1 over n squared. But you needed the cosmological constant to be exponentially small. And so from that analysis, it means that there is not enough. You cannot push this arbitrarily small. You cannot push it exponentially small. And so it means that there would not be enough degrees of freedom on the brane to get a sufficiently small cosmological constant. Right. Yeah. Okay, actually, maybe I should ask you. I should. Mm-hmm. Mm-hmm. Well, I thought that it's because the non-participative part depends on the G4 flex itself. So, right, so okay, so you would say that it would change the non-participative effects, but it would not turn it off. So right, okay, so the Harvard group would probably say that you would change the value at which you stabilize the Kähler moduli if you change, but then yeah. Right. But this is exactly where I'm going, right? So this is what I'm going to have a near horizon limit. Ah, okay. Right, then I'll speed up. So yeah, there is so okay. You there could have a flaw in the argument, and the flaw is that the Harvard group was taking a domain wall that is sourcing the KKLT ADS and declare that the UV degrees of freedom are the deformations of the special Lagrangian. Right. So this strategy works for the black holes, but you could compare what the CFT is giving you to the macroscopic result of the entropy. But here you don't have the entropy so to compare with. So how do you do? And so the idea is that you could, in principle, have hidden degrees of freedom. And in particular, at the brane intersections, you could have much more degrees of freedom. If I think about a D1, D5 system, the central charge is N1 times N5 and instead of N1 plus N5. And here, potentially, you could have degrees of freedom of the M2 branes ending on the N5 brane. So how do you account for that? And so, as Jose was saying, what you want to do is to evaluate the radius of a ADS in the UV that would correspond to the brane intersection. And so how do you get the ADS that would capture the degrees of freedom of the intersection? Well, locally, what you know is that you have a N5 brane on another M5 brane, and you have an M2 brane ending on this intersection. The M2 brane pulls on the world volume of the M5 brane. Essentially, it's the same as when you have a fundamental string ending on a D3 brane. The fundamental string pulls into the world volume of the D3 brane. And so from here, there's a supergravitic solution corresponding to this pool, whose infrared limit is a ADS3 cross S3 cross S3 warp product with a two-dimensional Riemann surface. So reading off the central charge here is quite hard, but it would be much easier in the type 2B version. But what we are going to do is to do something a bit easier, is that instead of thinking that we have this M2 brane ending at a single point, we propose to put this M2 brane charge ending on a cross shape on everywhere on the M5 brane. So then you would smear the M5 brane charge on the Z direction by assuming that the Z direction is compact, and then take the horizon limit, and then you can compute the central charge. Let me go quick on that. So there is a supergravity solution corresponding to this intersection. There's a metric ansatz, some harmonic functions, and M2 charge function. You can go to the near horizon limit, and the near horizon limit gives you a ADS3 cross S3 cross S3 cross T2. So the S3s here, they are given by the S3s of the M5 branes. The ADS is given by the time, by this common direction Y, and by U, where U is actually the product of these two radii. The T2 is given by Z, this domain world direction, and lambda, which is essentially the log of the difference of the logs of the radii. And then you can, once you have that, you can measure the central charge, which is proportional to N1 times N5, so number of 2 branes and 5 branes. And using the tadpole cancellation condition, this is proportional to the number of flux cubed. So this is bigger than what was found by the Hover group. And so this would give you a weaker bound on lambda due to the presence of the M2 branes. So now in the previous section, we did have a ADS3 with another ADS3. We could compare the UV and the IR ADS3s. But then you could say, but we smeared the branes, and so okay. But what would be the configuration with the most degrees of freedom? So essentially, is that we have many intersections, self-intersections of the special Lagrangian, right? So everywhere on the Calabi-Yau, but there could be a situation where all of the self-intersection come at the same point in the Calabi-Yau, and then there would be a like entropy enhancement somehow due to the M2 branes that end on the self-intersections. And so here, if you squeeze all of the branes at the same place, all of the self-intersections at the same place, this would be the configurations that have the most entropy. Right, so these configurations contain the maximum degrees of freedom one can get out of the branes. And again, it's possible to get a supergravity solution of this D3 NS5, D5 NS5 D3 intersection. And the solution has a near horizon limit that is ADS4 times S2 times S2 warp product with a two-dimensional Riemann surface. And it's possible to compute the ADS radius in four-dimensional Planck units. This time would scale like n to the power 4. And it turns out that there is a nice ADS-CFT correspondence. And so you could understand what is happening in the CFT. And this actually matches the free energy of the three-dimensional CFT. So if you just to show you, so this would be the quiver that corresponds to this brane section, is that essentially you could infinitesimally separate all of your 5 branes, and then you have a lot of degrees of freedom at this intersection. So to conclude, so we studied the domain wall configuration for the KKLT scenario. We assume that there exists a scale-separated ADS vacua from use for KKLT. We realized that by being sourced by this domain wall of M5 or D5 and S5 branes, we can use, so in principle, the C theorem would put a lower bound on the absolute value of lambda. So what we do is that we really want to have like compare an ADS with another ADS. So, okay, previously it was proposed to count the UV central charge by the possible deformations of the slag. But the problem is that maybe there is hidden degrees of freedom, and indeed the intuition was right. There is indeed more degrees of freedom than originally thought, and these new degrees of freedom actually correspond to these kind of Hanani-Witten-like degrees of freedom. So when you separate the 5 branes, then you would have a Hanani-Witten D3 brane that pops up. So these are the new degrees of freedom that account for this end power 4. So, however, because we are measuring the size of the ADS in the UV, we cannot put more degrees of freedom than this. And so there cannot be more degrees of freedom, and we would have the same conclusion as the Harvard group, that is to say that there is not enough degrees of freedom to get the ADS vacuum with exponentially suppressed cosmological constant for the KKLT scenario. So I think I'm done, so thank you for attention.